Let's unpack this. Imagine training a highly capable AI model, one that can tackle complex math problems or, write intricate code, reasoning through the steps just like we might.
Mm.
This kind of step-by-step thinking, often called chain-of-thought reasoning, is incredibly powerful. But teaching models to do it reliably, especially at scale, well, that's a huge challenge.
It really is. And one of the most promising ways researchers are training models for this kind of complex reasoning is using reinforcement learning with verifiable rewards, or RLVR.
RLVR.
Instead of just predicting the next word based purely on statistics, RLVR trains the model to produce outputs that actually work, like getting the correct answer to a math problem, for instance.
Okay.
The model gets a reward signal based on the verifiable outcome of its output. Did it solve it? Yes or no?
Right. So it's learning by basically by trying to achieve a specific goal. And the source material we're diving deep into today is a fascinating recent paper. It's titled Beyond the 80-20 Rule: High-Entropy Minority Tokens Drive Effective Reinforcement Learning for LLM Reasoning.
Yeah, it's a great one. This paper really zooms in on how RLVR is actually influencing the model's reasoning process. They're not just looking at the final answer, right or wrong.
No.
They're looking at the fundamental units the model generates, the individual tokens, like words or parts of words. They used state-of-the-art Qwen 3 models, the 8B, 14B, and 32B versions, and they trained them on math reasoning benchmarks using a method called DAPO, which is a specific kind of RLVR.
Okay, so the mission for this deep dive is to really dig into their analysis of, well, millions of these tokens and unpack a surprising, almost counterintuitive finding they made.
Exactly.
It points to a potentially much more efficient and effective way to train these reasoning models. The idea is focusing the learning signal on just a small, but apparently critical part of the model's output.
It's really insight into the mechanics of how these models learn to think.
Okay, so where do we start? Understanding the finding means understanding token entropy, right?
Exactly. And to understand their finding, we first need to get a handle on what they mean by token entropy. You can think of entropy here as a measure of the model's uncertainty or predictability when it's about to generate the next token.
Okay.
The model basically has a probability distribution over its entire vocabulary for what that next token could be.
So if the model is generating something like the capital of Francis, it's probably super certain the next token will be Paris, or maybe the first part of Paris. That's low entropy.
Precisely. Very low uncertainty, very predictable. But if it's at a point in, say, a math proof, where it could go down several valid reasoning paths, like deciding how to approach a tricky equation.
Oh, okay, yeah.
At a point like that, it might have a more spread out probability distribution over various potential next tokens, maybe logical connectors or starting points for different calculations, things like that.
So that would be higher entropy, more uncertainty.
That's it. High entropy means the model sees many possibilities as somewhat likely. Low entropy means it's very confident about just a few options, maybe even just one.
Got it. And the researchers, they analyzed the entropy for what? Over 1 million tokens generated during these step-by-step chain of thought processes. What did they actually find about this distribution? Was it even...
Well, this is the first big surprise. You can see it in Figure 2A of their paper.
Yeah.
You might intuitively expect the model's uncertainty to be, I don't know, somewhat evenly distributed or perhaps slightly skewed.
Yeah, maybe.
But they found it's extremely skewed, like massively skewed. A huge majority of tokens are generated with very low, often near zero, entropy. Only a distinct minority, a small fraction, exhibit high entropy.
Wow, really? So it's not like every token carries a little bit of uncertainty. Most of the time, the model is just executing steps it's really confident about.
Exactly. That's the beyond the 80-20 rule part they mentioned in the title. It's actually even more pronounced than 80-20.
Right.
They found that over half the tokens they analyzed had near zero entropy. Yeah, meaning the model was essentially deterministic about the next token. And only about 20% of the tokens had an entropy value above a certain threshold they used to mark the transition to higher uncertainty.
That's wild. So it paints this picture of reasoning as mostly following these highly predictable paths with only specific points, these little junctions where real uncertainty or choice comes into play. So the obvious next question is, what kind of tokens are these high entropy ones? What are they actually doing in the reasoning process?
Right, that's entropy pattern 2, which they explored visually in figures 2B, 2C, and also in those example visualizations later on, figures 12 through 17.
Okay.
They found that the low entropy tokens, the vast majority, shown in figure 2C, are typically things like Linguistic fillers, word endings.
Like aim or act.
Exactly. Or parts of mathematical expressions, numbers, or specific operational terms like simplify or frac for fraction, things that are very predictable once a path is chosen.
Okay, so completing a sentence, finishing a variable name, writing out a standard math operation, kind of the rote execution part once you're on a certain track.
Precisely. They are the predictable components within a given logical or mathematical sequence.
Yeah.
The high-entropy tokens, though, the ones in Figure 2b's word cloud, they look very different.
How so?
Their word cloud includes terms like wait, however, unless suggesting contrast or conditions. Then there's thus also indicating progression or adding points.
Logical connectors.
Yeah, and crucially, terms like since, because, for causality, and mathematical reasoning terms like suppose, assume, given, define, introducing assumptions or definitions.
Ah, I see it now. These sound exactly like the decision points or the crucial logical hinges in the reasoning chain. They signal a change in direction or the introduction of a premise or a point where the model has to actually choose how to connect ideas or proceed. These are the real forking tokens, as they call them.
Precisely. They represent moments where the model isn't just filling in the blanks, it's actively navigating the problem space. It might be considering alternatives or making a fundamental logical step forward.
And the higher entropy at these points makes total sense. Then there could be multiple valid ways to phrase a logical connection or introduce an assumption, or the model might genuinely be weighing different approaches.
Exactly right. And they did this neat experiment to confirm that high entropy really means something important is happening at these points, didn't they? Playing with the decoding temperature.
Yes, that experiment in Figure 3 was really key. So decoding temperature, that influences how much the model samples from its probability distribution, right? Higher temperature means more randomness, more exploration.
Yep. And they found that specifically increasing the temperature only for high entropy tokens during evaluation actually improved the model's performance.
Just for those tokens.
Just for those. Doing it for low entropy tokens, or even decreasing the temperature for high entropy ones, actually hurt performance.
Wow.
So it strongly supports this idea that higher uncertainty and sort of the ability to explore options at these specific forking points is crucial for good reasoning.
Okay, so we have this picture. Reasoning is mostly predictable segments, like train tracks, linked by these unpredictable high-entropy forks where the model makes key decisions. Now, you mentioned RLVR training earlier. How does that training process interact with these entropy patterns? Does it change them?
Right, so Section 4 of the paper looks into this, analyzing how entropy changes during the day-PO training, the RLVR method they used. The first finding was that RLVR largely preserves the basic entropy structure of the pre-trained model. You can see this in Table 1.
Preserves. Meaning what?
Meaning the tokens that were high entropy before training tend to stay in that high entropy group after training. The locations of the forks seem pretty stable.
Okay, so the points where the model is inherently uncertain or makes decisions are somewhat hardwired, maybe, by the initial pre-training.
To a significant degree, it seems so. The location of these decision points appears relatively stable. However, and this is really crucial, highlighted in Figures 4 and 5, RLVR training primarily alters the entropy of those already high entropy tokens.
Ah, okay. Not the low entropy ones.
Much less so. Tokens that started with higher entropy showed the largest increases in entropy after RLVR training, as seen in Figure 4. Low entropy tokens, conversely, remained very stable and low in entropy throughout training. Figure 5 shows how the lower percentiles of entropy barely budge.
Fascinating. So RLVR isn't just making the whole process like uniformly more or less uncertain. It's specifically targeting its influence to increase the uncertainty or maybe the flexibility at these key pre-identified high entropy forking points.
That's what the data strongly suggests. It's making the model more deliberate or perhaps more exploratory exactly where it needs to be decisive, where those forks occur.
The reinforcement signal, the reward for getting the right answer, seems to be predominantly driving changes in the model's policy at these moments of highest uncertainty.
It appears that way.
Okay, this is where it gets really interesting then. This observation, that RLVR seems to be naturally focusing its effect on the high entropy tokens, apparently sparked a pretty bold idea in the researchers. If RLVR naturally zooms in on these few crucial tokens anyway, what if you only train the model using the learning signal derived just from these high-entropy forking tokens? And just ignored the signals from the vast majority of low-entropy ones?
This is the core technical innovation they propose and test in Section 5.1. It's a really clever twist. They modified the standard policy gradient loss function used in reinforcement learning.
Mm.
Normally, the model learns from the gradient signal associated with generating every single token in the sequence that led to a reward.
Right. Okay. So every word, every symbol, every number contributes something to the learning update, whether it was a fork or not.
Exactly.
Yep.
But they introduced a filter. They essentially calculated the entropy for every token in a batch of generated reasoning steps. And then they used what they call an indicator function. You can think of it like an on-off switch.
Oh.
That switch was turned on only for tokens whose entropy was above a certain threshold. And this threshold was set dynamically for each batch to capture, for example, the top 20% most uncertain tokens in that batch.
So wait, the learning update, the actual adjustment to the model's policy based on whether it got the problem right or wrong?
Yeah.
That was only allowed to happen based on the gradient information from that small minority of high-entropy tokens.
That's it.
The 80% or more low-entropy tokens generated in that reasoning chain, their contribution to the learning signal was just zeroed out, thrown away.
Pretty much, yeah.
Yeah.
They're effectively telling the model, look, we're not going to reinforce or discourage you based on the vast majority of the predictable steps you take. We are only going to give you learning feedback based on the moments you were making a significant decision where you were most uncertain, where you chose a specific path at a logical fork.
That sounds incredibly almost counterintuitive from a traditional machine learning perspective. You think you need all the data points, all the signal you can get.
Right. You think more signal's always better.
So how did this focused training approach, using only the gradient from the high-entropy forks, actually perform? How did it compare to the standard vanilla training that uses all tokens?
Well, the results shown in Table 2 and figures like Figure 6 are quite striking, especially as they scaled up the models. Comparing vanilla DAO, which trains on all tokens, with their modified DPO using only the top 20% high-entropy tokens, they saw significant improvements in reasoning accuracy. They measured this using AA at 16.
Right, AMA at 16. And just to remind folks, AMA at 16 means accuracy within the first 16 attempts the model makes at solving the problem. It's a standard way to measure if the model can generate a correct solution among a set of possibilities it explores.
Precisely. And on the largest model they tested, the Qwen 332B, the gains were really substantial. On the AME24 benchmark, accuracy jumped by over 7 percentage points. It went from about 55.8% to 63.5%.
Wow, 7 points.
On the even tougher AME25 benchmark, the improvement was over 11 points, from around 45.6% up to 56.7%.
An 11-point leap on a hard math benchmark, just by changing which tokens contribute to the learning signal. That's a remarkable academic finding.
It really is. And Table 2 also shows something else interesting. This focused training generally resulted in longer responses on average.
Longer responses.
Yeah, which might indicate the model is exploring more detailed or perhaps more robust reasoning paths when it's trained this way. Figure 6 visualizes this quite well, showing the forking tokens only training curve consistently pulling ahead of the vanilla curve, especially on the larger models.
Okay, and you mentioned scaling. Did this benefit hold up or even increase for larger models?
Yes, Figure 8 shows a really clear and powerful scaling trend. The performance advantage you get from focusing training only on these forking tokens becomes more pronounced as the model size increases from 8B to 14B to 32B.
Interesting.
It strongly suggests this method is particularly effective at leveraging the increased capacity and complexity of larger language models.
So the bigger the model, the potentially more benefit you get from focusing its learning specifically on these key decision points. That's a very important implication for training the next generation of huge models, isn't it?
Absolutely. It suggests a path towards more efficient and effective training for the most capable models. They also did a sensitivity analysis, right? Testing how sensitive this was to the exact percentage of tokens included. Like, what if you use 10% or 30%?
They did, yeah, that's Figure 7. Using only the bottom 80% of low-entropy tokens, as you'd expect, drastically hurt performance. That confirms these high-entropy tokens are indeed carrying the critical learning signal.
Makes sense.
But the performance remains strong when including anywhere from the top 10% to the top 20% of tokens. So the method seems pretty robust. It doesn't require pinpointing the exact perfect percentage.
Good to know it's not super brittle.
And there was another finding about allowing the model to generate longer responses during training, helping even more.
Yes, that's in Figure 10. It suggests that extending the maximal allowed response length during this focused training on the 32B model led to further improvements. It kind of hints that focusing the learning signal allows the model to better utilize longer, more complex reasoning chains, which you often need for harder problems.
Maybe it learns to sustain its reasoning better. And they did quickly test this on a different model family, too, not just Quen, Llama 3.1.
They did, yeah. Figure 11 shows they applied the same approach, vanilla DPO versus forking tokens only DPO, to Llama 3.18b. Now, the overall accuracy was lower than the Quen models, which isn't too surprising. Different model, different base capabilities.
But the trend.
But they still observed the same trend. Training only on forking tokens outperformed the vanilla DPO that used all tokens. It's initial evidence, but it suggests this finding isn't just some weird quirk of the Quen architecture. The underlying principle might generalize.
Okay, so let's step back. We've gone through the entropy patterns, the RLVR effects, the core innovation, the results. What does this all mean for you, the listener, who uses or is interested in these powerful LLMs? Why does this kind of, deep dive into token-level mechanics actually matter?
Well, I think this research provides a really fundamental, you could say more academic, insight into the learning dynamics of reasoning in LLMs, especially when trained with these RLVR methods. It clearly shows that not all parts of a generated reasoning chain contribute equally to effective learning.
Right.
There's this critical minority of tokens, the high-entropy forks, where the model's policy decisions seem to be most impactful for learning generalized reasoning skills.
It really challenges that intuitive idea that you need to reinforce every single correct step the model takes. Instead, it seems the crucial learning happens when the model is actively navigating uncertainty or making a key logical jump at these forks.
Exactly. And the paper discusses why this might be so effective. One hypothesis they mention in discussion 1 is that focusing RL on these forking tokens helps preserve or maybe even increase the model's flexibility at these decision points.
Okay, flexibility. As opposed to what?
As opposed to methods like standard supervised fine-tuning, or SFT. SFT can make models very good at replicating patterns they saw in the training data, but sometimes that can lead to them being less flexible when faced with novel problems.
Right. Which some other research has suggested can sometimes feel more like the model is memorizing solutions rather than truly learning to generalize the reasoning process.
Precisely. By focusing the reinforcement learning pressure on the forks, you're essentially training the model on how to make good decisions when it's faced with uncertainty or choices. And that skill is vital for generalizing to new, unseen reasoning problems.
You're reinforcing the exploratory decision-making aspect of its policy, not just the deterministic execution of known steps.
Well put. That connection back to generalization is really insightful, I think. It makes intuitive sense that training the model on the moments it's truly deciding, rather than just executing a known sequence, would lead to better performance on novel problems it hasn't seen before.
Yeah, it does.
And their second discussion point, discussion 2, highlights something unique about LLMs. It contrasts the kind of entropy patterns we see in LLM chain of thought with what you might see in more traditional RL problems.
How so?
In many traditional RL setups, the agent's actions might have, more uniformly distributed entropy, but LLMs are different. They combine this massive pre-trained knowledge base, which makes a lot of language generation of basic steps feel very low entropy, almost deterministic.
Like filling in common phrases or simple calculations.
Right. They combine that with the need for deliberate higher entropy exploration at these critical logical decision points, these forks. This sort of bimodal entropy distribution we see in LLM reasoning chains might be precisely why targeting the high entropy minority is such an effective academic approach. It really leverages the specific nature of how these models are built and trained.
That's a fascinating point. It's not just about RL, it's about RL applied to this specific kind of system with its mix of stored knowledge and decision-making needs. This really raises a huge question for me. If this principle, focusing the learning signal on high-entropy decision-making moments, is so effective for RLVR, could it be applied elsewhere? Could it improve other training methods? Maybe change how we approach supervised fine-tuning for reasoning tasks, or even influence how we prompt or interact with these models during inference?
It definitely opens up some really exciting avenues for future research, doesn't it? Understanding where the most critical learning happens seems key to designing more efficient and ultimately more effective training strategies down the line. This deep dive into token-level entropy provides a clear academic signal about where those crucial points might be.
So to sum up this deep dive then, this research powerfully suggests that when training large language models for complex reasoning using reinforcement learning, we can make the process significantly more effective. The key is focusing the learning signal not on every single token generated,
but specifically on that minority of high-entropy tokens that represent the key decision points, the forks, in the reasoning process. Doing this seems to lead to better reasoning, especially for the larger, more capable models.
It's a really potent demonstration that understanding the internal dynamics of LLMs at a granular level, like looking at token entropy, can uncover fundamental mechanisms driving their capabilities. And importantly, it can point towards innovative, more academically rigorous ways to train them better.
Absolutely. It's about getting smarter with how we apply the learning signals.
Okay, so here's a final provocative thought for you, the listener, to mull over. If training on just, say, 20% of the tokens, the most uncertain ones, can yield such significant gains in reasoning ability, essentially making the learning process much more efficient by targeting the signal precisely. What other hidden efficiencies or crucial learning signals might we discover by continuing to look closely, maybe in unconventional ways, at the internal processes and outputs of these incredibly complex, often opaque models? What stands out to you from this deep dive?